I'm truly honored to have this opportunity to talk here at MIT today about a project that I started years ago when I was a PhD student of Mike Dertuzos in 1970. Our weekly meetings, we talked about semantic networks which operated analogously to the pressures and flows of hydraulic systems. We imagined problem solvers structured isomorphically to the topologies of the problems they solved. I didn't get the PhD, but I did spend my career in engineering. I worked in teams of engineers building virtual realities for torpedoes and the world's largest scalable fabrics, both for multiprocessors and routers. But now, with all this industrial experience under my belt, I want to resubmit my thesis proposal. I've developed these concepts significantly since and have gotten many interesting things working in a simulator called the Fractal Workbench. There is nothing like simulation to drive the magic out of a dream and turn it into equations. My purpose here today is to infect you with these ideas that Mike Dertuzos and Marvin Minsky exposed me to all those years ago. Everything about Have and Want is on braingears.blogspot.com. Papers, videos, presentations, interviews. These are some of the questions that drive this work. I want to find this magical intelligence putty stuff that you could spread over your motors and sensors and they would work better for it. Currently, I have a set of 4 abilities that are built into Have and Want elements that allow learning to occur naturally, like water vapor freezing to form a snowflake. The Have and Want schemata is my latest reformulation of these networks. It has a dozen or so distinct atomic forms, each good at doing something. We'll show how links between atoms are formed and how to build larger semantic networks hierarchically. What are these networks capable of computing? To give you a feeling of this, we'll show some fixed networks analyzing toy examples. We use toy models to describe interactions succinctly, hoping that they can be made robust later. The first example shows how bidirectional logic can be used to turn a statement inside out. We'll describe the max-or element, which performs the winner-take-all in this bidirectional environment. We'll see how trees of max-or elements can service unlimited numbers of inputs and still do the same function. Then we'll describe how auxiliary information can be added to a bid so it can represent many mutually exclusive events. This construction implements an intentional mechanism that obeys Maslow's hierarchies of needs. We'll show you an element that computes the Hamming distance and use that to make a distributed associative memory. And the final example is a shaft transducer. The transducer learns by adding new elements to recognize unrecognized coincidences. Other more advanced forms of learning are compacting representations and volume optimizations. And unfortunately, I don't think we'll have much time to talk about them today. The Have and Want brain is composed of nodes and fractal links, connected in an ordered graph where the lowest nodes are connected to the world through motors and sensors, and the more sophisticated nodes are at the higher in the graph. At the top are the being's beliefs and knowledge about the world. Nodes connect sparsely to other nodes. All information about the world is held in these fractal links. A brain with any common sense might have thousands to millions of them. Each fractal link represents a particular world state, which we will refer to here as its fact. For example, the link might represent it is red. But be clear, the facts exist in us as we try to understand, not the machine as it computes. Each link has two scalar variables. The have, this is what is in the link, the have that the fact is true in the perceived world. It goes up and it's commonly shown in green. The want signal connotes that the being has motivation to make the fact true. It goes down and is commonly shown in red. What might these up and down variables encode? There seems to be three classes. The first comes from Bayesian prediction with their pi and lambda variables. Then there is a class of pairs of dual conjugate variables, often related in energy. Pressure flow machines might use them to guarantee stability. Note that both of these are linear, and actually that's a limitation. The final group is nonlinear. It uses the logic of the excluded middle. Humans probably do that too. And these are some of the pairs that seem to have worked. We'll go through them more in a second. These are the simplest atomic forms, the kind of tinker toys which you'd buy from the store and put together to make bigger networks. They're shared fractals, divide the have and want signals of a single bit in various ways, using shares of various kinds. There's a previous unit which keeps around state from the past, allowing associations about state transitions to be made. It also manages simulations. The gate modulates up and down signals, making them more or less poignant to the computation. The mirror says when at the top, what you have is what you want, and at the bottom, what you want is what you have. This is kind of an optimism that is almost zen. Bundles or groups of one-bit forms, variables are a special case. This is where we're headed, but we're not there yet. This is a simple Super Mario Brothers environment, but let's go to something more simple. Let's start with a simple network. The halves compute as they flow up. If it's raining and I have an umbrella, I'll stay dry. But the logic can be turned inside out. If it's raining and I want to stay dry, then I want an umbrella. Now, if umbrella B is closer, I want umbrella B. A Maxor gate implements a winner-take-all. It uses a logic of the excluded middle as follows. Its have signals flow up as the maximum of the workers have. A single winner is determined, and then the desire goes down to the one winner, and no one gets anything else. So we can build these into trees, where the tree operates pretty much like the individual elements. Here's a movie of it operating. Let me let it start. If you put this input C up, you can see the sensation flow up to the top, and then if you put desire, it goes back down to C. Now, if you make another input higher, the desire goes back to that input. So basically, you have the tree operates and designates the biggest, tells the biggest that it's biggest. That would presumably enable him to do something. We can expand a Maxor tree by adding an auxiliary bundle of information characterizing the bid. These could come from different sources of information: audio, video, touch. The biggest bid wins, and it promotes its information to the top. The auxiliary information establishes kind of a two-way communication between the top and the selected item. The top can manipulate the state in the selected item and then move on to another As the auxiliary information goes up the tree, it may change its form. Bindings can be frozen into the network. Okay. This is a bidirectional multiply AND gate at the heart of an associated memory. It's used to record encountered products. Its upward half signal is the product of the worker's half signal. The credit for distributing desire is based on a Hamming distance as computed by minus log of half. It measures how much each worker lags. The desire going down is split proportionally. An example has the rightmost worker lagging at 0.1. And that goes up to the top, but credit comes down, and it all goes to the lagging worker. Now we can use these multiply AND gates to create a network which acts as an associative memory. Consider what happens when an input pattern is presented which almost matches one product. The halves go up, and the turb wins, and that turn goes to the top. Now, if someone desires there to be a match, that comes down and it says, you better give me more of this third variable, and then I'll be at this. So in this way, associative memories can actually predict future actions. We hope to show how large, sparse, distributed associative memories can be built using bidirectional logic of the excluded middle. Okay. We'll show how learning grows on top of a known basis. Our example is of a rotating shaft whose angle is modeled in the brain by a set of three fractals, A, B, and C. As the basis for inductive learning, we assume that there's a transistor already in place that reports the angle the shaft has and can want it to be at a different angle. We will now show how rotations are learned. The first step is to add a previous atoms to each bit to hold previous values. Then associations are allowed to grow as we assume it experiences left-going rotations first and right ones going second. Using temporal coherence-based algorithms, we think two clusters can be detected. Before concluding, I'd like to show you an earlier video where new distinctions were added as they were experienced. There is still no conclusion slide. And thank you for your attention.